Advances in Financial Machine Learning. Based on the research of Marcos Lopez de Prado, let's turn investing from an art into a science. Most investment failures are not bad luck. They are the predictable result of doing science badly. The traditional firm hires star portfolio managers, hands each one capital, and hopes their intuition produces alpha. But this lone genius model is a silo, irreproducible, impossible to debug, and when one blows up, no one can explain why. There is no specialization, no division of labor, no peer review, and no independent validation, the very things that make real science reliable. The fix is to run investing like a laboratory, not a one-person workshop. So Lopez de Prado borrows the idea that powers modern industries: division of labor and co-specialization on an assembly line. No single person builds an entire car or iPhone, and no single person should build a whole strategy. Raw data enters and is refined at 6 specialized, auditable stations: data curation, feature analysis, strategy development, backtesting, deployment, and portfolio oversight, until it emerges as a systematic investment agent. Let's walk the line, station by station. The line begins with data curation. First, everything must be point in time. You may only use the data as it was actually known at the moment of the decision. A figure that gets restated months later cannot be fed back into the past, or you leak the future into your model. Second, how we sample matters. Markets deliver information in irregular bursts, yet time bars sample on a fixed clock, oversampling quiet periods and undersampling the action. Instead, form dollar, volume, or tick bars that sample by activity. Their returns are far closer to the well-behaved bell curve that statistics assumes. Next, feature analysis turns clean data into learnable signals. The triple barrier method labels each observation by the first barrier it touches, a profit-taking level, a stop loss, or a time limit, so the label reflects how the trade would truly have played out. Trend scanning fits many look-forward horizons and keeps the one with the strongest statistical significance. Then comes one of the author's signature ideas: meta-labeling, also known as corrective AI. Let a primary model choose the side of the bet, long or short, and let a second model decide the size, betting big only when it is confident. Finally, because labels overlap in time, we purge training samples that overlap the test set and add an embargo afterward, restoring genuine independence between train and test. Strategy development is where features become a refutable investment thesis, and this is where causality matters. Correlation is not causation. Two variables can move together only because a hidden confounder drives them both. Causal discovery recovers that structure, the graph of what actually causes what, directly from the data. Causal inference then asks a sharper question: what happens if we intervene? By eliminating non-causal associations, we can estimate the true premium due to a particular risk factor. Without this causal analysis, it is not possible to form a risk-return optimal portfolio. Backtesting is a validation step, not a search tool, and it must be done by an independent function. First, walk-forward testing trains on the past and tests forward, then rolls ahead. Second, combinatorial purged cross-validation goes further. It recombines folds many ways to produce a whole distribution of out-of sample paths instead of a single path that can be easily overfit. Third, we can also search the grid of profit-taking and stop-loss levels for the optimal trading rule. And fourth, using combinatorially symmetric cross-validation, we measure the probability of backtest overfitting. How often the strategy that looked best in sample actually underperforms out of sample. A high value means the strategy is likely monetizing a spurious pattern. Deployment is production engineering. Live data is messy, so the first job is quality control: detect and impute missing observations, and identify and clip outliers before they poison the model. Then comes speed. Heavy computations are parallelized across many workers. Slow Python loops are replaced by vectorized array operations, and rolling quantities are updated incrementally. Recomputing from scratch is order n work every step, while a good incremental update is order 1. Together, these make the strategy fast, robust, and safe to run in real time. Finally, portfolio oversight allocates capital and watches for danger. Classic mean variance optimization is notoriously unstable. A tiny change in the inputs produces wildly swinging weights. Hierarchical risk parity instead clusters assets by a correlation tree and allocates down the hierarchy for stable, diversified portfolios. Nested clustered optimization optimizes within clusters and then across them. Monte Carlo optimization selection tests each allocator and scores their robustness to a particular data-generating process. This replaces allocation to assets with an allocation to allocators, hence achieving diversification across model risk, not only across asset risk. Meanwhile, structural break tests, such as CUSUM and the Supremum augmented Dickey-Fuller statistic watch for explosive regime shifts, flagging a break the moment the evidence crosses its critical threshold. Step back and the whole machine is visible. The assembly line replaces the star manager with a scientific process at industrial scale. Each station is specialized, testable, and improvable. Data is carefully transformed as it travels through the assembly line, and the output of one station is the input to the next. The payoff is not a few black box strategies. It is a process that produces strategies you can trust at a predictable rate, reproducible, auditable, and with numerous checks and balances. That is how investing moves from craft to science. These ideas are developed in Marcos Lopez de Prado's books, Advances in Financial Machine Learning and Machine Learning for Asset Managers. As Professor Campbell Harvey writes, machine learning is the second wave of quantitative innovation and will touch every aspect of finance. And as Professor Frank Fabozzi puts it, this is the first book to explain why standard machine learning fails in finance and to provide the solutions.